Hey guys, this is K.Sudharshan here to present my experimental analysis about the study of a light dependent resistance, or otherwise known as LDR. So, the aim of the experiment was to analyze the behavior of the light dependent resistance using the given apparatus. So, apparatus given was basically consisted of a voltmeter, ammeter, and the LDR as such. It is a basic apparatus. It is a basic Ohm's law setup that you would use. This is like a circuit diagram showing how the apparatus was schematically set up. The yellow lines show the light falling on the LDR. And hypothetically, the LDR's resistance is supposed to vary with the intensity of light. The LDR is an electronic opto sensor. Basically, it alters an electric characteristic, that is resistance, in the presence of light. So basically, what we can see in the experiment too, that the resistance varies with the intensity of light. So when the amount of light falling on the sensor varies an electric characteristic. In this case, the electric resistance or the conductance of the LDR is varied. The resistance is very high under dark conditions and low under bright cases. We'll test this out in our experiment while we double the intensity and check it out. The device consists of a wavy track of cadmium sulfide between metal contacts, so as to increase. So basically, this is schematically how the device should look. Alright, there's like a more zoomed in version. There are metal contacts over here. This wavy nature between the metal contacts would actually increase the surface area of light falling on this film. Alright, this is basically me showing how the experiment is done. I'm turning on the flashlight and keeping it close to the LDR so that light falls on the LDR and the resistance. There is significant resistance change over there. You can see where the LDR is. Right now, I go on with the experiment by changing the voltage values. The resolution of the voltmeter over here is 0.01 volt, and the resolution of the ammeter is 0.01 milliampere. So as I change the voltage, you can see there is like a significant change, very small change over here in this case though. There's like a change in the ampere readings. For 0.5 volts, I got like a 0.01 milliampere reading. Now I change it to 1 and I find the reading to be 0.02. The same can be if I keep repeating the experiment. I'll get like a series of values, which when I linearly regress should provide me the right result. So we'll keep looking at the experiment. We'll keep taking readings. Now the maximum output, the range of the output in this voltmeter is 3 volt. So we'll be heading back to values below 3 volts. You can see that like with one intensity, one light, the resistance is pretty much high, but that is like for the given input voltage, the output current is kind of very low. Right? So resistance is pretty high in inference. So I'm taking 2 more readings. Yep. So you can see we have taken readings over here, and I'm noting on the resolution to be 0.01 milliamperes in the meter side, and this is 0.01 volts in the voltmeter side. Alright. Basically, we plot these values, the values that we have noted, which you can see in the next few slides, and we'll draw a graph to show the ohmic behavior of these. Alright. Now what we are trying to do is I have added another torch like flashlight over here, so as to kind of in a sense double the intensity falling on the LDR. Now we'll try to note the readings of the voltmeter and the ammeter as such, basically like the ohms law, of course, and we'll try to find the resistance in this case. Now I change the voltmeter readings over here. Let me write the serial numbers down so that I can note properly. Yeah, so at 0.3, around 0.3 volts, I get a reading of 0.01 milliampere. 0.6, I get a reading of 0.02. 0.9, I get a reading of 0.03. So basically you can see the linear behavior coming out in this case. Let's not judge the experiment, we'll keep performing it right now. 1.5, we should get 0.05. So you can see the linear behavior over here, right? Yeah, so I'll keep heading on and taking the readings. You can guess the resistance to be almost around 30 kilo ohms, I guess. This basically shows the linear response of the LDR, and the output provided by the LDR is given it is linear and almost intercepting at 0. We can consider the output of the LDR to be ohmic as such, right? Then we'll also see how the intensity of the LDR is related to so we have taken 8 readings till 2.4 volts and we observe linear behavior in these cases. We'll try to plot these graphs and we'll try to note the readings, and we also observe here, we'll observe the intensity reduces the resistance by half. Doubling the intensity reduces the resistance by half, that is. Here I have tabulated the results that I have obtained from the experiment and before. You can see the values taken over here in terms of volts and milliamperes. The resolution of the voltmeter was 0.01, but since I have taken values close to 0.5, I have noted down in that sense. And then the resolution of the ammeter as such, the current was 0.01 milliamperes. So, and out of which I got these values tabulated. Plotting these, I was able to linearly regress them to get the slope to be around 63.26 kilo ohms. The intercept of this line over here, if I draw a line, straight line through the predicted values, intercepts would almost cut the y-axis at a value of minus 0.00217, and the r-square fit is 0.9 for showing a really good fit for my analysis curve over here. This case is done for the first part of the experiment, where I used only one torch. So basically one intensity is halved. In the part 2 of the observation, what we observe, this is for twice the intensity, right? So we have double the intensity in this case, and from here we observe like voltmeter and the ammeter readings, the same resolution as before. This is like a more ideal case. We observe the intercept to be exactly at 0 and the slope to be perfectly like 30 kilo ohms, and the r square fit was perfectly 1. Of course, you can see all these values form a straight line as such. This shows perfect ohmic behavior for the LDR. This is what kind of separates it from a photoresistor, in the sense that the intensity in a photoresistor, it's rather the reverse current produced by the intensity of the light falling on it in reverse bias, and in this case it's the voltage, it is the change in the resistance value by itself as such produced. This is more like an intrinsic case for the semiconductor, right? Inferences. So we observe linear behavior in both cases corresponding to the Ohm's law. They have an intercept almost at 0. We saw in both the cases the graphs were linear and almost touching 0. We also observe the resistance to be 63 kilo ohms in case 1, almost 63, almost, it's not accurate, while being 30 kilo ohms in case 2. That is an error associated with this, of course. And while being 30 kilo ohms in case 2. Case 2 being the scenario with double intensity, it is justified that the resistance reduces with increase in intensity of light falling on it. Basically, the conductivity doubles with intensity. We can also see that since we double the intensity of light, the resistance reduced by almost half the values. Basically, what I was trying to say. We showed to that resistance is inversely proportional to the intensity of light falling on it. Yes. The results and innovation. So hence we have analyzed the characteristics of an LDR. We have finally analyzed the characteristics of an LDR. And we can hence kind of extrapolate the applications of an LDR. Of course, LDR can be used for light intensity detection and measurement. Obviously, from the way we have done the experiment, we can understand the intensity is pretty much the highlight of the LDR. The difference between LDR and photodetector is that the photodetector works on the principles of reverse current and yeah, basically what I was trying to say before. The LDRs can be used for motion detection. So if there is this is some idea that I thought of. If there is an intensity drop in incoming radiation, the resistance would increase, and hence applying a Schmidt trigger or anything that would actually drip or something. So we can basically use it as a switch, like say you're walking past a door or something, and there's an LDR added to a light source, and you walk in front of the light source, blocking the light, and hence dropping the intensity, causing an increase in resistance, and hence cutting off the current, which basically makes it work as a switch. So, concluding my experiment, I would like to thank you for watching my video. And so concluding is, I would like to summarize what we have done. We have basically set up circuit to analyze LDR characteristics. We have performed the experiment and noted ohmic behavior, and also thought of possible applications. For LDR. Yep. So pondering on these thoughts, I would like to sign off from the presentation. Thank you.